Hi everyone, I'm Alessandro Melloni and I'll present the work on evaluating anonymity of onion routing, done in collaboration with Martijn Stijmen and Øyvind Idrehus. Tor is the software implementation of the onion routing protocol. That is a low-latency anonymous communication network, allowing users to connect to destinations without revealing their identity. Everything they need is a piece of software running on their machines called Onion Proxy, allowing them to connect to the Tor network, composed of thousands of servers around the world. It works by creating an encrypted channel to a first node called guard node, and then by extending it to a middle node and an exit node that finally connects to the end destination. This path is called a circuit and it carries bidirectional traffic and is not message-based. Each node peels off a layer of encryption and that's why it's called onion routing. At any given time, a lot of users connect to a lot of different destinations through the Tor network, and that's where the idea of hiding among the masses comes from. Since it was presented, researchers have been interested in studying and analyzing what happens when some of the nodes are corrupted. For example, the guard node and the exit node. In such settings, Tor designers state that the protocol doesn't offer any privacy at all, but research on attacks shows that while the anonymity can be indeed broken, it's far from trivial. Research on defenses shows that by changing or adapting the protocol, the goal can be made even harder. Finally, there are some formal security notions in which the onion routing protocol is provably secure. So, we identified a gap between formal approaches and real-world results from results in low-latency ACNs. We provide an evaluation framework for the anonymization attacks and defenses on the onion routing protocol. The two main types of attack on the onion routing protocol are traffic analysis and website fingerprinting. The first is about an attacker capturing both the ingress traffic, that is, the traffic going into the Tor network, and egress traffic, that is, traffic leaving the Tor network. And they are interested in matching each traffic trace of the ingress traffic to the corresponding traffic trace of the egress traffic. Here, the graphs show the bandwidth in bit per second, depending on time t. Website fingerprinting, on the other hand, is about an adversary identifying the destination based on the fingerprint, due to some unique features in the traffic pattern of its destination. Our framework is based on the interaction between an adversary and the network, and we use several random variables, here on gold background, to capture the different aspects of the game. We use random variables to have a greater control over the settings of the evaluation, so we can avoid to rely on some unspecified sample statistics. S represent the secret of the game, that is, which users are connected to which destination. G is determined by S through protocol specification, for example, the length of the circuits. G contains all the information of the game, including the traffic traces. V is determined by G, and it represents the view that the adversary has of the game. Z captures all auxiliary information available to the adversary, for example, traffic patterns used to train their machine learning algorithm. The goal of the adversary is captured by the query Q, that might contain also a target T. The query processing here is what is usually referred as an attack on Tor, and is the processing of the information contained in V to obtain an output random variable O, while taking into consideration the auxiliary information Z and the goal Q. The evaluator can then compute a metric μQ on the secret and the output random variable. We can now make some examples. DeepCore by Nasr et al. Is a traffic analysis attack. There are n users connecting to n different destinations. S can be seen as represented as a bipartite graph, which parts are the set of users and set of destinations. G contains the state of the game, and V represents the view of the adversary. In this case, the adversary captures the traffic between the user and the guard node, and between the exit node and the destination, and they want to match, for each ingress traffic trace, the corresponding egress traffic trace. Another example is the deep fingerprinting attack by Serena et al. In these settings, a single user connects to a single destination, and the adversary wants to verify whether such destination belongs to a specific subset of the set of all destinations. This specific subset is the target and is part of the query. In this case, the view of the adversary is only the traffic between the user and the guard node. The adversary of the two examples had different goals, and this is closely related to the idea of privacy notion. Historically, privacy notions have been based on indistinguishability for message-based scenarios, where an adversary interacts with one of two copies of the network and they need to identify which one, in a similar fashion to cryptographic games. The figure of the right represents the relations and chain of implications between a lot of different formal privacy notions in the model done by Kuhn et al. Unfortunately, such formal privacy notions have a limited applicability to onion routing, because indistinguishability is too ambitious as a goal for real life, making the adversary unrealistic. The onion routing is circuit-based due to the requirement of low latency instead of message-based, and the adversary's information in the security game is different compared to the information that the adversary obtains in the real-world application, where the metadata is sometimes more important than the data itself. Our interpretation of privacy notions is based on unobservability and unlinkability, usually expressed in terms of the bipartite graph representing the secret S. In user destination unobservability, the adversary can learn the total degree of the graph, that is, the cardinality of the set of the edges, but they cannot learn any endpoint of any edge. In user destination unlinkability, that is the main goal of the onion routing protocol, the adversary can know the degree of each node, that is, whether they are connected to the Tor network or not, but there cannot be any edge for which they know both endpoints. In user unobservability, the degree of the destinations can be known to the adversary, while the degree of the users must be kept secret. This models a scenario where the users don't want the adversary to know whether they are using the Tor network or not. Vice versa for destination unobservability. We identified 4 different types of security goals, namely distinguishing, decisional, classification, and computational. Distinguishing goals have been mentioned previously, and they are characterized by an adversary interacting with one of 2 copies of the network, and they need to identify which one. Each copy of the network is equally likely to happen, and there is no intrinsic meaning attached to any of them. Decisional goals allow the prior probability distribution to be non-uniform and possibly also to have intrinsic meaning attached to the outcome of the network, namely positive or negative. Classification goals are about an adversary trying to classify which one of multiple networks is interacting with, while computational goals are the most general ones, and they might be characterized by a non-single correct answer. For example, a greedy adversary trying to de-anonymize as many users as possible. The first example that we saw earlier, that is the traffic analysis case of DeepCore, is a classification goal while instantiated in the single instance, because the adversary has a single ingress traffic trace between the user and the guard node, and they want to classify it with the corresponding egress traffic trace captured between the exit node and the end destination. On the other hand, the deep fingerprinting attack is a case of decisional goal, because the adversary is interested in identifying whether the end destination belongs to a specific subset of the set of destinations without determining precisely which one. Once the goal is set, we need to measure how well the adversary is achieving it. And that's where anonymity metrics come into play. According to Siverson, anonymity metrics should not depend on unknown parameters for which reliable prediction can be made. They should reflect the effort that the adversary has to put in to break the anonymity or privacy offered by the protocol, and as a consequence, these anonymity metrics focus more on single real-life attacks, more than our interpretation of using anonymity metrics to evaluate algorithmic attacks. To do that, they need to either relate to the adversarial effort, or they need to capture the information content that is available to the adversaries to be processed. As such, they can depend on estimated parameters as long as they reflect the influence that these parameters have on the metrics themselves. Moreover, they need to be efficiently computable, and they also need to be robust, meaning that they can't exhibit any pathological or counterintuitive behavior. Finally, they need to be adapted to the different type of goals. We identify two main categories of anonymity metrics: input and output dependent metrics. Input dependent metrics depend on the secret S, the state of the game G, and the view of the adversary V. They are called input dependent metrics because the view of the adversary V is usually the input for the attack. They rely on concepts from information theory, such as entropy, conditional entropy, and mutual information, and they're usually used to evaluate defenses, because defenses try to minimize the amount of information that the adversary is able to collect in their random variable V. On the other hand, output-dependent metrics depend on the secret S and the output O, or their respective version SQ and OQ. Some common anonymity metrics for decisional goals are precision and recall, but they suffer from the base rate fallacy. Accuracy is the usual metric for classification goals, but it suffers from biases in the dataset. Computational goals have various anonymity metrics associated to them, but they suffer from a not always straightforward applicability to real-world scenarios. The last part of our framework is the threat model, and we need to refer to the protocol specification to have a relevant description of the view of the adversary V. The figure shows a typical Tor circuit composed of the onion proxy, the guard, the middle, and the exit nodes that finally connects to the destination. Due to the protocol specification, each of these nodes have a different view of the traffic they carry. For example, Tor multiplexes multiple connections to different end destinations over the same circuit. Each of these connections is called a stream. So, onion proxy and the exit node have a visibility of the single streams, while the guard node and the middle node carry the circuit and have no visibility of how many streams they are actually transporting. Now that we have all the information, it's time to apply our framework. We start by defining the support of S, that is the set of users and set of destinations, and the probability distribution. S determines G through protocol specification. So in case we are evaluating a defense, we need to take that into consideration as well. The threat model allows us to have a relevant description of the view of the adversary V, and the query Q captures the goal of the adversary. It's important to have a clear definition of all the random variables to help reproducibility of the results and comparison between different approaches. Lastly, the evaluator can compute the metric μQ of SO, in case if it's an output metric, and this is possible because they have a greater knowledge of the game compared to the adversary that knows only V. To conclude, we introduced a new framework to evaluate research results in low latency SCNs, requiring explicit assumption on the environment, explicit definition of adversarial goals, the choice of relevant metrics, and explicit definition of the threat model, allowing for meaningful comparisons of different results, including their limitations. We identified some of open problems related to the framework, for example, the integration of other onion routing features, for instance, hidden services or leaky pipes, and the expansion to the dynamic case of our framework by including the dependency on the time variable t. This allows, for example, the adversary to interact with the Tor network itself, or for example, for users to join and leave the network after the experiment started. That was all. Thanks for your attention.